G'day, in this video we're going to be looking at some early models of light. In inquiry question 1 we focused on the basic principles of what is light, and I guess the purpose of that was to segue from everything that we learned about in module 6 to then talk about the beginnings of module 7 and the connection between electromagnetism and light. Our focus was looking at how the speed of light has been measured, how that helped to support Maxwell's theoretical mathematical models, which helped to show that light was an electromagnetic wave. And we also began to briefly introduce how light can be used to learn about the world around us. And so all of those concepts set us up for Module 7 and into Module 8 as well. However, for inquiry question 2, we're going to go back in time a little bit, and we're going to be looking at the evidence that supported the classical wave model of light and the predictions that can be made with it. And we're going to start today by looking at dot point 7.2.3, which looks at experimental evidence that supported the models of light proposed by Newton and Huygens. So some key learning intentions today, we're going to be looking at Newton and Huygens' model of light. We're going to evaluate the models based on how they explain observed phenomena. So we're going to be looking at whether or not those models can explain why light reflects, refracts, disperses, and diffracts. So Newton's model of light. Isaac Newton was known for his corpuscle theory. He suggested that light is composed of small particles that he called corpuscles, that light had mass and obeys the laws of physics like any other particle, that particles are so small that if you cross two beams of light that they would not collide and scatter. And I guess this was used as a way to explain a very easy counter, I guess, to make for this model of light, which is that if you point two beams of light into each other, well, why don't they crash into each other and interfere if they're made of mass? And he just said that they're really small, so they don't collide. Now, this model might seem a little bit odd and weird at first inspection, particularly because so far we've mostly focused on light being a wave, not being made of mass and matter, and it being a particle. Now, interestingly, in this topic, we'll actually look at the idea that Newton wasn't all that far off, at least in general principle. However, his theory didn't get very far in his time and after that, simply because there was a lot of physics and understanding that was missing to actually show how his theory actually linked to what we know about light in its particulars. It should also be noted that Newton's model of light, when it was introduced, was quite widely accepted because of the reputation that he already had and the stature that he had in the scientific community. Now, Newton's model of light was quite good at explaining some of the basics. Things like we cast a shadow because the particles hit a particular surface and they don't go any further, and so we don't get light anywhere else, therefore we see shadows. It was also really good at explaining reflection, that light is composed of small particles, corpuscles, that light has mass and obeys the law of physics like any other particle. Therefore, when we have corpuscles moving into a surface, they reflect directly off and obey the law of reflection. And he used quite a simple classical physics explanation to show what was going on here, that essentially, at all times, the particles had the same horizontal component of velocity, that there was a vertical component as well, and in the beginning it was pointing towards a reflective surface, and at the end it pointed directly away from the reflective surface, and that because this collision was elastic, that these two horizontal vectors, while opposite in direction and anti-parallel, were equal in magnitude. Therefore, we had two vectors of equal magnitude as well, which again helps to explain mathematically why we get two equivalent angles. When explaining refraction, again, he used a very simple vector-based proposal to explain what was happening and why. Again, this horizontal component was going to have two vectors of equal magnitude that was not going to change. But if we went from a rarer to a denser medium, the vertical component would change. And to explain why there was an inward bend, Newton concluded that the vertical component of velocity and or force had to increase once the object moved into the denser medium. What this implied was that this medium here pulled the matter and caused an acceleration, and that caused an increase in velocity. So Newton effectively was trying to explain that if you say had light go through from air to water, that it would travel faster through the water. It should be noted that this is not the case, and we'll talk about that a little bit later, that Newton was trying to make his theory simply just fit the already known observations. The decisions that were being made about this theory, whether they actually made sense or not, simply just tried to match up with what the experimental evidence of the day suggested. To explain dispersion, we are still looking at refraction, but here what he stated was that corpuscles of different sizes would correspond to their color, and this explained why white light that dispersed refracted by different amounts. There was a positive to what he was stating. First off, he was concluding that white light was actually made of constituent colors, and this was helpful and useful to our understanding of light and improved models of light from there forward. And interestingly, this kind of explanation only built on Newtonian physics as Newton understood it. Essentially, the idea was that for waves of light that refracted less, this is because the particle was more massive. So you may have had a force being applied onto the particle to pull it inwards, say by your glass prism. However, because the object that was being pulled was more massive, it didn't cause as much acceleration and therefore not the same change in velocity that, say, one of these smaller particles experienced. Already, I'm hoping that you're coming up with a few different limitations that work quite oppositely or against Newton's model of light. And the first thing is that light travels slower in air. That's not a very great statement to make. We now know that light is slowed down through essentially those denser mediums, and it was proven by an experiment by Foucault, who was able to repeat his rotating mirror experiment that we talked about a few lessons back. But instead of the light traveling through air from the rotating mirror to the stationary mirror, he let it travel through water instead. And he was able to conclude that the light, in fact, did travel slower through water rather than faster. And it was actually this experiment that really tore down Newton's model of light and moved people towards appreciating a little bit more the concepts around the wave model of light. Furthermore, we've seen in plenty of scenarios that light can both be reflected and refracted simultaneously off the same surface. And Newton's model did not have anything available to help explain this phenomena at all. He could not explain why some particles that were made of matter would be able to bounce off a surface and why some particles that were supposedly identical were able to pass through. Furthermore, his particle theory, which was all about the idea that particles move in straight lines, couldn't explain a concept like diffraction, where once we get around a barrier, they kind of spread out again. He could also not explain polarization and interference. And the big fundamental thing here that kind of didn't help Newton's case was that there was no real experimental evidence to support his theory, particularly the part about the particle size and diffraction. So while he did come up with a few good explanations that made sense based on his prior learnings of classical physics, experimental evidence wasn't really there to back him up. So this moves us to Huygens' light model. So Christian Huygens came up with wave theory around the same time as Newton. However, his work was nowhere near as popular because he didn't share the popularity that Newton had. As such, this theory was overlooked for quite a while. But as Newton's theory started to wane a little bit, this model of the wave theory came to become a little bit more mainstream and popular. Essentially, Huygens said that there were these point sources of waves and they radiated out these little wavelets, which is probably best shown here, that these point sources emit these individual sets of wavelets, and that essentially at the ends of these wavelets, if you joined up all of the tangents, you would end up with what we would call a wavefront. And depending on the geometry and how you're drawing the diagram, these wavefronts may be presented as straight, flat lines, sort of moving across, so to speak. If we're radiating out from a single source in all directions, it may start to look a little bit more circular. And then, of course, in 3 dimensions, you could also visualize this a little bit more in 3 dimensions, forming these spherical wavefronts. Now, in class, we're going to be looking at Huygens' light model in a little bit more detail and focus on having a look at this simulation in particular to give a lot of visualization of what's going on. But what this animation is trying to show here is that we have these wave fronts that are moving into a surface, and that may lead to these points of wavelets generated, which essentially is leading to reflection, which we can see here. Essentially, this line here and this wavefront here are perpendicular to each other, which is showing this idea of reflection. We also have a set of wavelets here that are going in a slightly different direction when we are looking at the wave fronts. And this is because refraction is occurring when we're going from a less dense to a denser medium. And when that's happening, what we're seeing is the wavelets start to move a little bit slower than the wavelets that are moving through the air. And thus, that's causing a different angle in the resulting wavefront. It's a little bit complex to look at, but when you actually start drawing it out, and again, when we start looking at some of the visuals that go along with it, with a little bit more of a detailed set of animations in the simulation than this one, it will start to click in and make a little bit more sense. The key bit here, though, is that there are these successive wave fronts that are all moving in a certain direction. They're being generated by these wavelets, and depending on the interaction between each of the individual wavelets and their position and their speed, you're going to end up with wave fronts that are moving at different speeds and are going to be moving at different angles. And this kind of explanation is really good at explaining how reflection and refraction actually occurs, and better yet, is a really good way of explaining how reflection and refraction can occur at the boundary between two surfaces at the same time. Huygens' model also does a really good job of explaining diffraction. So essentially, when you get your wavefront, which is moving along and ends up passing a barrier, when we get around this barrier, we've got these point sources that are propagating waves even further. And when they do so, each of their little wavelets are able to spread out beyond the barrier itself, which explains then why we end up with these wave fronts which are curved in nature, and we experience and see the diffraction where waves are able to bend around a barrier. When we get into class, we're going to unpack these concepts even further and really give them a bit more scrutiny and analysis. But when we get to the next video after we've looked at that in class, what we're going to be focusing on a little bit more is the concept of diffraction and how it was harnessed in Young's double slit experiment, but then particularly how diffraction as a concept was then able to help explain Huygens' light model itself. But until then, have a good one.